What's going on, everybody? Today's video, what are we doing? And what are we talking about? Today I've got, yet again, something very rare, very cool. This is a development cartridge for the Sega Genesis, or the Sega Megadrive, for those of you that are in the UK. Made by the company Western Technologies Incorporated. Actually quite sophisticated. It's got a couple of pieces of software that came with it for MS-DOS. And there was one software program called Sega Load, and that allowed you to just quickly test a ROM that you were working on and had compiled. As well, there was a full-blown Sega-branded 68K software debugger. So this is pretty cool about this unit. It's pretty awesome. I haven't been able to fully explore all of the functionality of this unit, but it does come with a disassembly window that allows you to set breakpoints, check and test different areas of memory, including registers and some of the VDP and all the different registers that are available as part of the Sega Genesis console. We're going to dive in and check out the hardware, and I'm also going to go and review some of the software and show you guys how that all works. So it's a pretty cool dev unit, so I'm excited to show it to you guys. So without further ado, let's get this video started. Here we go. So as you can see, the development cartridge was actually quite large. It had the option of interfacing a 32 megabit memory expansion daughter board onto the flash cartridge. With the daughter board removed, you can see a series of SRAM memory chips, 2 EEPROM chips for storing the development cartridge firmware, as well as several 7400 series logic devices which served as memory control and data bus latching. There were also 3 unpopulated DIP sockets, which served as an interface port for connecting the memory expansion board. By flipping over the daughter board, you can see the interface pins on the back side. These would simply line up and interface to the unpopulated DIP sockets. On the back side of the board, there was a 36-pin parallel interface port for connecting a development PC, as well as an IDC port for connecting a debug line coming from a modified Sega Genesis console. The modification involved connecting an interrupt signal from the Sega Genesis CPU processor, and this provided functionality for breakpoints and allowing the system to halt the CPU and allowing monitoring of memory and different registers. Next, we connect the parallel cable to the development PC. And as you can see here, I've inserted an LED breakout box, allowing us to monitor the activity on the data bus lines. One thing to notice is that there is a 5-volt signal coming from the parallel interface cable, but does not provide enough current to power both the console and the development cartridge. So just be sure to connect the DC power pack for your Genesis console. Now, I did have some issues getting the cross-compiler working for this unit. It was recommended by Western Technologies to use the Sierra C 68K compiler. According to the documentation, it was recommending that this be set up as a cross-compiler with GCC. So I started looking into that, and it seemed, having to completely regenerate and recompile a version of GCC and setting up that cross-compiler properly. It seemed to be quite a daunting task, and so I had checked around with a few different people. It just seemed a little bit more involved than I was willing to commit. What I ended up doing was just actually calling the cross-compiler executables, the binaries, directly using a batch file. And, I'd looked online and a few people were doing this. Essentially what you're doing is you're just bypassing the make file for GCC completely. And so I just created my own batch file, enabled all of the different parameters and the settings required to properly compile my source code for the Genesis into a ROM file that I can load and test on this SRAM development cartridge. So I'll pop over to the Windows 98 PC and I'll show you guys some of that code and some of the batch files and the commands that I use there. What we're going to look at today is the Sega dev folder. on my local C drive. And this is where I have the Sega programs for loading ROMs, as well as the 68K software debugger and all of my source code. This is where I stored everything. So the first one we're going to try is Sega Load, and we're going to test out a ROM that I have stored, a backup ROM. Now I've created a couple of batch files for us to test, and the first one that we have is just a Sega dev test. So my batch file here simply prompts the user to enter the file name of the ROM file with its extension, and that saves that into the input variable, and then it will call the Sega Load program followed by the folder path and the bin file name. That's it. Okay, so we'll activate that, and we get prompted to type the name of the ROM file that we want to load. So in this case, we're going to type in sonic.bin. And we hit enter. It loads the program, and then it will load that information, the binary file, into the SRAM of the development cartridge, and it will automatically run that ROM. Now, some of you might assume that all I had to do to get this unit to work was to plug in the cartridge into the console, hook up the parallel cable to the development PC, and then activate the console power. Well, that was definitely not the case. I had a lot of issues trying to get this unit to work properly. So first off, the EEPROM chips, which stored the firmware for this device, were missing. So these were likely pulled for recycling. And so I had to try and track down a copy of the firmware for this unit. I was lucky enough to find a website where a previous owner had dumped the images of these EEPROMs, and as well had a copy of the MS-DOS software that was used to communicate with the unit. So that was a stroke of luck. Once I had reprogrammed 2 new EEPROM chips, I was able to move forward and try to debug the parallel communication port, which I had a lot of issues there as well. And now if you look at some of the photos here, you'll notice that the board I received had some modifications performed to it. There was a transistor and a resistor applied, as well as several bridge wires and traces that had been cut. Now, after looking at these modifications, I started to realize that these modifications were actually preventing the board from functioning properly. So I was trying to analyze and try to understand why these modifications had been performed, and to me they did not make sense logically. There were VCC lines that had been cut, certain address lines were being rerouted to certain areas, to ground or to VCC, which did not make sense to me at all. After analyzing the board and the different components on this unit, I noticed an inscription on the back side of the daughter board. And it reads, "Install this board only on a Genesis development card REV D or newer. Older Genesis development cards REV C must be modified per a schematic before installation or upgrade." So right away that got me thinking, because the revision of board that I obtained was a REV D. So after thinking about this a little bit, I came to the conclusion that it was possible that these modifications were performed to a REV D model board when they were intended for a REV C model or older. And so that these modifications were in fact prohibiting the unit from booting up properly. So I double checked everything and reconnected things in the way that I thought that the unit would be able to function correctly. And sure enough, I managed to get this board to boot up and communicate with the development PC. So we're going to run the Sega 68K software debugger, and we do that by entering the Sega dev command into the command prompt. And as long as your parallel port is connected properly, it will load the following screen. And now what we'll do is we'll go and load a source code project. And we go up to the File menu and select Download File, rom1.out file. This is the debug output file. And this was created as part of the Sierra C compiler. And I'll be showing you guys that as well in a moment. So now if we open up this program, so now there our project has been loaded. So we have a memory dump window, which essentially shows us the ROM file in a hex viewer. That's essentially what we're seeing there. So now if I just go and simply scroll down here on our memory dump window, we should be able to see some of the header information and some of the ASCII code that I have entered in there as part of this project. So we'll just scroll down, and there you can see some of that ASCII information that I have stored there. So it shows the Sega Genesis dev, the year, as well as the title of this ROM, which is Jerry's Sega Code. This is just a test. So that's pretty basic, straightforward. The disassembly window is showing us all of the different commands that are being executed as part of this program in this ROM. As well, we have our register information at the bottom. And if we run and execute this program, we can actually monitor these registers and the information that is being stored there. And we can actually also see the commands being executed in real time while the program is running. We can go and run a test here quickly. So if I go up and say run and say animate, so you'll see how the program is running, and you'll see the address is changing from 252 250, and then it's moving down into different move commands. Register information is changing on screen in real time. And so this is just part of this basic Hello World program that we're testing here today. So as you can see, it's bouncing back and forth between 2.5C and 2.5E. So now if I actually escape this program and we remember 2.5C as our address, and if we load this program again, if I scroll down to address 2.5C for a breakpoint, I simply double click. So line 2.5C is the breakpoint on our program. So now if we were to run this program and say run to breakpoint, and there you go. And so the program immediately halted at line 2.5C, and it also displays all of our register information here at the bottom for developers to run some checks and confirm that memory is what it should be reading, and allowing them to debug. Now you can see here our symbols window. This also shows the many different source files that we have as part of this project and the different symbols that are being used with this program. So as you can see, we have several assembly source code files as well as our demo.c source code file. Now the watch window, we can essentially add, if we right click here, we should be able to add a watch address if we wanted to monitor a specific area of memory. But there's all sorts of different functions, but we won't be going over that today. I might do a later video showing more in-depth functionality. So that's pretty much it. That's the basic part of it. But as you can see, for those of you that are really into Sega Genesis and different Sega console programming, there's the VDP, which is the display processor, I believe. And there's all these different options here that are available for looking at register and editing parts of that RAM for testing different functions and making sure that the programs are working as they should be. So we'll go ahead and close the Sega debugger, and we're going to go and look at the demo program, the source code for it, and as well look at the Sierra C cross compiler. So one of the C files that we have for this project is demo.c. originally written by Jeff Fort from Western Technologies Incorporated. This was back in the early 90s, of course, as part of this demo. Now, as you can see, I've gone in and modified some of the original code that was put in by Mr. Jeff Fort. Originally, he had a single ASCII message being printed, and I went ahead and added a couple of different lines. So it's pretty straightforward. We have a couple of include files as well as some variable declarations. And then our main is very simple. We have a Sega logo command to print the logo on screen, followed by a couple of ASCII messages being printed on. And we have declaration of some variables there to control the cursor location prior to us printing any information on screen. So I've added my own little message there. It's just a little joke there. But again, it's just an example, a very simple example of the C source code being used with this project. And here we have one of the original assembly source code files, logo.s. For those of you that are familiar with Sega Genesis source code, this may be familiar to you. It's simply an array of hexadecimal values to specify addresses and data for the character set. And here we have the Sega logo. And there's, as you can see, there's quite a bit of it for all the different characters. Would be interesting to go in and potentially try to change some of the character information being used as part of the Sega logo, which would be kind of interesting to test out and play around with. But anyhow, so I just wanted to quickly show you guys some of the C and assembly source code files that were used with the project. So we'll go ahead and close this, and we'll take a look at the Sierra C cross compiler. So this is my batch file here, and this again is not using the make command with a makefile. I've bypassed the makefile process because I'm not using the GCC compiler. So what I'm doing is I'm just going in, calling the binaries that are associated with this cross compiler. I'm just going in and calling them directly with their associated parameters to make sure that I compile and assemble and link my source code in order for it to function properly with the Genesis. So as you can see, the first thing I do is I go in and erase any old output files or debug output files. That's the first thing I do, just to clean things up a little bit. From there, I go in and compile and assemble my C source code files. And that's the first two steps that I do there. And from there, I go in and compile all of my assembly source code files. And once that is complete, I then link them all together and generate the ROM file, the binary ROM file, as well as the debug output file. And that's all generated as part of this batch file. The last step calls Sega Load, and to boot up the project here that we have rom1.out. And that will load this project into our SRAM memory on our development cartridge. So let's go ahead and run this, and I have a shortcut on the start bar down here for us to run, which will then compile all of our source code and load it into the SRAM memory of the development cartridge. It did that very quickly and loaded our rom1.out file. And so as you can see there, Jerry's Sega code test, but indeed. Anyway, it's a pretty cool little unit, pretty handy to have if you're someone that's doing homebrew. So if you ever do get, have the opportunity to get your hands on one of these, it's a pretty awesome little unit to have in your collection. So that wraps the video today, guys. Thanks again for watching. And for those of you that want to help support the work that I'm doing here and allow me to create more content on a regular basis, I'm hoping you guys can join my supporters page. So the link is above and it's also in the description. And as a dedicated supporter, you gain access to special content and different links that I'll provide in your account section. So you just log in and you'll have access to that content. So again, thanks again for watching, guys. Hit the like and subscribe if you can. I do appreciate it, as always, and I thank you. So we'll see you guys in the next video. Take it easy. Ciao.